Alright guys, this is topic 59 here, and this is going to be a lot shorter than last one. So this is definite integrals, so it's a limit of Riemann sums. Now before we actually start getting into that, we're going to prove this property here that says that if you have a constant with a function, you can get that constant out of the integral and it's going to be the same answer. Alright, so right here, notice that they're asking us to prove the integral of 2x dx is equal to 2 times the integral of x dx. Okay, so notice this right here is the 2x function, right? We start at 0 and a slope of 2, so up 2 over 1, so on. And this one right here is the function x. Oh, excuse me. Okay, so if we get to take the integral between 0 and 2, all that means is we're going to find the area between 0 and 2. Alright, so if we find the area of this triangle, by the way, you can wait on this graph. You don't even have to do this graph if you don't want to. It's just a representation of what's going to happen with this example 2. So we're going to find the area of this and find the area of also this. We know that the area for this one, see, the area for this one is 1/2, well, let me write it over here. We have that this is 1/2. Let's see, the base is 2 and the height is 4, so we have 1/2 times 2 times 4. And we're asking ourselves, is that equal to 2 times 1/2? Let's see, in this case the base and the height, they're both 2. See, times 2 times 2. As you can see ahead of time, hopefully, that you're going to find out that it is the same. Okay, so this is going to be 4 is equal to 4. So it works. Now on example 2, this is just review basically. On this one right here, all we're going to do, since this is a little bit more difficult, what we can do is we can actually get the 4/7 out. Right? If you think about it like this, if you factor out a 4 out of the top, okay, then that would give you this 4 that I'm talking about here. I would have x plus 2 dx, and to find the integral between 2 and 5. Okay, so this and this is the same thing. Now this is it's a lot easier to do. Alright, so notice that this x plus 2, this is this picture right here, and the integral between 2 and 5 is to find the area between 2 and 5. So this is the area right here. Now if you look at it, this is a trapezoid on its side where, no, I'm sorry, this is not a trapezoid on its side. Let's see. Yeah, it is. This would be base 1, this would be base 2, and the height would be, let's see, 1, 2, 3. Okay, so the area of a trapezoid, if you remember, you can find that by doing 1/2 base 1 plus base 2 times the height. Okay, so again, this is a trapezoid. So that will give you 4/7. 4/7 came from here, and then this inside of that becomes 33/2, and that will give you 66/7. Okay, so the big idea here, that it's not really has nothing to do with that, but the big idea here is if you have a Riemann sum and you take that Riemann sum, you have an infinite amount of intervals. Alright, what that means is that each one of these rectangles is getting smaller and smaller and smaller and smaller. Well, if you have smaller rectangles, then the smaller these rectangles are, the closer you are to actually approximating the integral of this. Alright, so if you have an infinite amount of rectangles between, in this case, A and B, okay, if you have an infinite amount between those, then that's going to give you the definite integral. Okay, so again, the Riemann sum, if you take that to infinity, gives you the definite integral. And I'm probably going to put a video up. There's This, I don't feel like this does a good job of explaining how it works, but I'll put a video up there to a link if you want to see how that works. Okay, so all right, so let's take a look now. Yeah, let's not even do this. It's not even worth it. So hopefully you understand how to do this. If you're looking for a left sum, okay, the left sum in this case would be that point, that point, that point, that point. So if you notice, the differences between the width of those rectangles is 1/2. And I don't really know what this function is, so I don't really know. I don't really know exactly what the height of this is, except for just to say that they're going to be located at those points right there. And sorry, I cut off a bracket there. There's a bracket over there. Now, if we were writing the definite integral for the above, right? So if we were finding the definite integral between, in this case, it looks like between 1 and 3, okay? Because there's that 3 right there. There's that 1. We would write it like this. And since I don't know what the function is, so I'm just going to have to write f of x dx. Alright, so that's that. Alright, let's look in the back here, and we're not going to do all of the back, we're just going to do example 4. Example 5 I found to be not very useful. So, on example 4, alright, they're asking you to write this as a definite integral. Now notice that you're taking the limit as n goes to infinity. So this is actually very easy, alright? When you take this to infinity, that becomes from a to b, the definite integral between a and b, and this little ck's and this ck just become x's. So we have 7x squared plus cx all over 3 dx, and that's it. There's nothing else to it. We're not going to do this example 5, but we will take a look at one from your homework just to kind of quickly talk about it. I'm not actually going to write it down, but I've wrote it down ahead of time. This is 59 homework. Now on this one right here, they're asking you for the using the right rule. All right, so you're actually doing the right point. So on this one right here, same thing as always. We don't have, you can graph it if you want to, but it's just going to take you more time. If I'm trying to do this, the first thing I have to find is delta x. Remember, that came from subtracting 4 minus 1 divided by the number of subdivision or intervals. In this case, they have 5. So the width of those rectangles is going to be 3/5. Alright, so what I recommend you doing is you're going to have a number line between 1 and 4. Notice that 20 over 5 is 4. And then you have 1 plus 3/5, which is 8/5. And you keep adding 3/5, 3/5, 3/5 until you get to that. Alright, now if I'm looking for the right-hand rule, I apologize, the right endpoint. Okay, what I'm going to do here is I'm not going to use this one because this is to my left, so I'm going to use that one, this one, and pretty much all the way to 4. Okay, so notice that's what I have. The heights are the y value at 8/5, 11/5, 14 over 5, 17, blah, blah, blah. All right, and if you do that, all you have to do, just like I showed you in the past, just grab your calculator, you know, let's clear that off, and then we have the natural log. Oh, yeah, this one's interesting. Now I know why I picked it. We have the natural log of x, x cubed, and then we're going to square that. Okay, so notice that that's the way I had to write it, even though this is natural log square. So this is the same thing. All right. So now, what we're gonna have then is we're gonna go to second, calculate, and we'll go to value. Press enter. And it's gonna give us some kind of weird looking graph there, and then we're just gonna put a divided by 5 and see I get the number that I have here. And without you even leaving the screen, just go to the next one. 11 over 5. There's that number, and so on and so on. Okay, now, and that's going to give me this. Now, if I were looking for the left the left endpoint, then I would actually start with 1. So I would have f of 1, f of 8/5, f of blah blah blah, all the way until f of 17/5. Okay, so just make sure that makes sense. You can see the answer for the next one, not on mine, is the same idea. Now on this one they're asking us for the left. So when I do the number line here, I'm going to start with 0. 0, 1, 2, 3, and 4, then I stop at 4. Alright, anyways, good luck. I hope this is not too difficult for you. If you got any questions, remember to tweet at me. I should be available for some questions. Goodbye.